Bismillah ar-Rahman ar-Rahim. Now we are going to go to the kinematics of this motion. We're going to talk about transverse waves, and specifically we're going to look at the positions of these particles. As you can see, they are moving up and down, so their position will be represented by y, because y generally are the vertical axis. Okay, so we're going to look at these particles here. As you can see them, there are many of them, maybe a million of them in a string, and we are going to write the equation of motion, or let's say the position or displacement of the particle as a function of time. As you can see in this string here, these particles and this particle and this particle at this time, you see, they have different positions. Okay, so the particle itself is important, and then that particle starts moving as a function of time. Okay, so as you can see, the motion is sinusoidal. You can see it's clearly sinusoidal. Okay, so it has, so my equation for the position of the particle, we have to define two variables. Why we have to define two variables? Because we have to know which particle we are dealing with, because as I told you, there are many particles you can see, and each particle is moving differently from the other particle. Okay, so I have to know which particle we are talking about. So X represents the particle itself, and T represents the time the particle now, that particle is moving. Okay, so we look at its position on the y-axis as a function of time for that specific particle. So that equation is equal to Ym, the maximum amplitude, the maximum displacement, or the maximum position, which is called the amplitude, which is this point here. You see, for example, in this animation, the amplitude is 1 centimeter. You can see it. The particle goes up to 1 centimeter and comes down to -1 centimeter. So that's why M, the maximum position or the maximum displacement from the origin, or the maximum, it's called the amplitude. Okay, it's called the amplitude. Then we write sine, because it is sinusoidal. You can see it clearly. Sine kx plus or minus omega t plus phi. Let's now define. There are things which are constant, and there are things which are varying. The things which are varying are x and t. The things which are constant is omega, is ym, k, which is called the wave number, omega, which is called the angular frequency, and phi, which is called the phase constant. And this whole thing here is called the phase. Okay, it's called the phase, and this here is called the phase constant. The phase constant. This is the angular frequency. Okay, and this is called the wave number. The wave number. Now, let us now define things. So let's define a thing. Okay, and this is the amplitude here. Of course, this is the amplitude. The amplitude is clear. Okay, the amplitude, as we said, the maximum displacement from the origin, or the maximum position here, which is 1 centimeter in this animation, or it's called the amplitude. Okay. Now, so y here, to find a number here, we need to know k, omega, phi, ym, and then we need to put the x, the position x here will define the particle itself. If we are looking for this particle here, we have to look at x, put this value of x, then we will define this particle. So the x will define the particle. T is the time as the particle is moving up and down. The time will be varying. Okay. All right. So this is called the displacement. Displacement or position from the displacement or position. Okay, from the origin. That's the displacement. This is exactly in Physics 101. You have seen an equation like this: x equal v0t plus half at squared. What was this x here? It was the position of displacement. Okay, from the origin. So this is for waves. sinusoidal wave, and this is for a particle moving in a straight line. So yeah, what I mean here, this is the position or displacement of the particle, okay, along the y-axis. You can see the particle is moving up and down. We define now k is 2 pi over lambda. And we have to define what is lambda now, and omega is 2 pi f, okay. This is called the wave number, it's written there, and lambda is actually what we call the wavelength. Wavelength. Now what is a wave number? The wave number is defined as how many wavelengths you have in 2 pi meter. If you look at 2 pi meters, a distance of 2 pi meters, how many wavelengths? If in 2 pi you have only one wavelength, your k is 1. If in 2 pi you have two wavelengths, your k will be 2. And so on. So k is actually the number of wavelengths you have in 2 pi meters. A definition, okay? Okay? It's called the wave number. It has units, of course. It has a units of meter minus 1, okay? Meter minus 1. And now lambda, which has the units of meter, is called the wavelength. Let me show you where is the wavelength in this illustration here. The wavelength is a distance. It's a distance, first of all, it's in meter. It's a distance along the x-axis here between two identical points on the wave, okay? For example, this point here and this point are identical because they will be moving together, whether they are moving up or down, okay? They are moving together. This point here and this point are not identical because if this point is moving up, this will be moving down, okay? I said two identical points. These are two identical points, this one and this one, because they will be moving up and down together at the same time. Okay? So any two identical points, the distance between them is called the wavelength. And it is in meter. Okay? All right? You can, for example, look here. For example, in this figure here, the wavelength, if this is the origin 0, from here to here you can see is about 3.2 centimeter, if this is centimeter, okay? So the wavelength here is 3.2 centimeters. You can measure it also from here to here. Okay? It will be 3.2 centimeters. It's constant. The wavelength, whether you measure it from here to here, or from here to here, or from here to here, it's constant. Okay? So that's the wavelength. And we know what is the wave number. You can notice that here, the units of this here is radian. Because actually this is radian per meter, and this is meter, so the units here is radian. Similarly for here, this is radian per second, and this is the second, so it will be radian. So the whole thing here, phi is also in radian, so the whole thing, the phase will be in radian. Okay? So we talked about the wavelength, which is the distance between two identical points on the wave. We talked about the wave number, which are the number of wavelengths you have in 2 pi meter. Now we talk about the angular frequency and the frequency. Of course, the frequency, this angular frequency will be second minus 1 or radian per second, and this is and the f is called the frequency, is defined as the number of oscillations per second, and this is hertz. The units is hertz, okay, and so omega is called the angular frequency. It comes here is 2 pi f, okay. The frequency f is the number of oscillations or vibrations per second. The wavelength is the distance between two identical points on the wave. The wave number and angular frequency are defined. Phi here will be the phase constant, will be defined by the initial conditions, okay? So phi is defined by the initial condition. Initial conditions. The figure that the figure I showed you before about the string, which when the figure was not moving, we call this a snapshot. Okay, we call that one a snapshot. Okay, we can also draw here, since we have two variables, x and t. We can draw y versus t. Here in this case, in the snapshot, time was fixed. Okay. Here we're going to fix the position of the particle and look at that particle, how it moves with time. So it will look something like this, okay, as a function of time. It will be also oscillatory. And this is the particle. The particle, of course, is moving up and down. This is ym, and this is minus ym. Okay? By the way, the maximum position is called a crest, and the minimum position is called the trough. These are some definitions that you should know, okay? Crest and trough. For example, but here, this is a crest and this is a trough, okay? Now, the time, so the particle is moving from this, let's say from this position, from ym at t equal to 0, when it reaches this point, this is the time it has spent, okay? When it goes to this point here, the time will be read from here. This is the time, okay? Okay. When it goes back here, this will be the time here. When it comes back here, this is the time. So the time from here to here, when it goes from one point, go down and come back to that point, it's going from here, goes down and comes to that point. That is called the period, okay? It's called the period of oscillations. Is a time, first of all, it is a time, It's a time for one complete oscillation, okay? One complete oscillation. T is in seconds, units is in seconds, is a time for one complete oscillation. Oscillation, okay? Okay. Of course, the frequency and the period are related, something that you know before. F is equal 1 over t. They are inversely related, okay? This is the number of oscillation per second. This is the time for one oscillation, okay? So these are related by this equation here. This kind of wave, when you see the time here, we call them traveling waves, okay? You can also have waves, because of the time here, we call them traveling waves, and the form will be this form like this, as you can see it here, okay? This is the form, it has kx plus or minus omega t. Of course, the plus or minus here has a meaning. If the wave can be moving to the right or to the left, as I showed you before. In this case here, the wave is moving, it was moving to the right. So if the wave is moving to the right, we have to put a minus sign, okay? And if the wave is moving to the left, the sign will be plus. So you can, by looking at the equation of this wave, the equation here, you can tell in which direction the wave is moving, okay? I just want to clarify one thing here. As you can see, this is called a snapshot. It means here time is frozen. We are not changing the time. As you can see, this particle in green and this particle in green and this particle in green, they have different positions. So y here is actually this distance from the origin down. This particle has a negative y. Its position will be negative. This particle also, is closer to 0. It's somewhere here. This particle here has a position positive. It's very close to the amplitude, as you can see. So when I move from this one particle to another, I'm changing the x here. Okay? I'm changing the x. So x here is defined for me the particle. If I say x equal 2 centimeter, I go to 2 centimeter and I look at this particle here and how it's moving up and down. So time is varying and x is, so x represent the particle itself we are talking about, okay? That's the x which comes here. And then t is varying. In this figure here, t is also fixed. So t is fixed and s is fixed, and you have only a single y. Y, the position of this particle is only one value. But when t is changing, the particle will be moving up and down. It has different positions along the y-axis or displacement, different displacement or positions as a function of time. Okay? Very, very important. Thank you.